What's up, Cal Gang? Welcome back to some statics. So today we're going to be learning shear and moment diagrams. So shear and moment diagrams are a way that we express shear and moment basically throughout a beam. So say we have a beam, right? As we're going to get into some more practice problems later. There's going to be a shear and a moment force acting throughout that beam, right? As you go further, it might be greater or it might be smaller than it is at certain points. So that's how we're going to represent it, is with a diagram basically. And so really quick, before we start jumping into the problems where I'm going to explain it more to you, I like to remember the convention for shear and moment. So if you take the cut, right, when we're taking shear and moment, we're going to take a cut on the beam. If we take a cut and we cut off all of the right side, that's what we're doing on D's side here. Say we're looking at a beam that's like this. And say we're going to cut off here and we're going to cut everything over here. The shear is going to be pointing downward and the moment is going to be curled upward. But then say we cut here and we look at this side of the beam, then we're going to take our shear to go upward and our moment to go upward. So you can kind of imagine moment is always pointing upward, whereas shear is down from the left, up from the right. So let's go ahead now and just jump into some practice problems and figure out how to do these diagrams. All right, so here we are with the first problem. So we're given a beam that's in the wall, right? It's an internal support on the wall at A. It's 4 meters long and has this 8 kilonewton force acting at the end of it. So very simple beam going on here. Now we need to find the shear and moment diagrams for this beam. So let's go ahead and get started. So first of all, we need to figure out the support reactions at A, because we're going to take the shear and moment diagrams starting from A, and X is going to be going outward this direction. This means that before we can draw the shear diagram, we need to basically figure out all the unknowns. So to do that, let's start with the force body diagram. We know that this is 4 meters long, and let's draw in all of our forces. So we have the 8 kilonewton force pushing down. Then of course at A, we have a rigid support in the wall. So it's going to have 3 reactions. It's going to have A of Y, A of X, and the moment at A, which we're going to draw like this. That's what we have here. So now let's go ahead and find them. First of all, looking at the system, if we were to do sum of the forces in the X, we're going to find that A of X is equal to 0. Very simple. Because there's no other forces acting in the X direction and we're in equilibrium, so sum of the forces in the X has to equal 0. Then if we do sum of the forces in the Y, set that equal to 0, we're going to find A of Y minus 8 is equal to 0, and we're going to find that A of Y is equal to 8 kilonewtons. Then we need to find moment at A. So what is moment at A? So let's sum up the forces, set them equal to 0. So this moment we drew is a negative moment, so we're going to subtract moment at A. And then this 8 kilonewton force, right, that's making us want to rotate clockwise around A. So we're going to have to subtract that 8 kilonewton force times its distance, 4 meters. You're going to find that moment at A is equal to negative 32 kilonewton meters. So this just means negative 32 kilonewton meters. We drew the moment the wrong way. It should be going counterclockwise instead. So there we go, we found the support reaction. So now we can go ahead and try to draw these out. So what we're going to do is we're going to take a cut, basically. And the cut can be anywhere. So we're just going to take an imaginary cut. Let's just imagine we're taking a cut here. So when we take the cut, we're going to have the forces, right? We're going to have shear, or this is going to be normal, right? Normal, we're not worried about normal, but we are worried about shear, right? And shear, let's look at the convention. Shear points downward if we're taking a cut from the left side. So shear is going to point downward. And then of course our moment is also going to be there too. So we can define this in terms of X. So let me draw a new one. Instead of looking at that masterpiece, let's draw another force body diagram. So this time we're going a distance X out. We don't know how far this distance is. It could be 0, or it could be 4, or it could be anything in between. But we're going to label that a distance of X. So then, like I drew over here, we're not worried about normal because we're just trying to draw the shear and moment diagram. So shear is going to point downward. There are moments, it's going to point like that. Then of course we have our reactions on the wall, A of Y and moment of A. So A of Y is 8 kilonewtons. So that's going to be here, we can label that 8 kilonewtons. And then moment at A we said is negative 32, so we can just draw it going this way at 32 kilonewton meters. So then, all we have to do is write out equations for E and M. So if we want to find what V is, right, we can just take sum of the forces in the y. We know it's equal to 0, right? We're at equilibrium. So if we go ahead and do this, we have 8 pointing upwards, and we have V pointing downwards, so we're going to subtract V. So this is our moment, or our shear here, so that equal to 0. So then if we want to write this over, we can go V is equal to 8 kilonewtons. So what this is telling us, basically, is that no matter how far we are in the beam, right, we could be at 1 meter, we could be at 2 meters, we could be all the way at 4 meters. Our shear in the beam is going to be equal to 8 kilonewtons, right, and it's going to be pointing downward. But then let's draw the moment. So to find the moment anywhere in the beam, we're going to take sum of the moments around that point and set it equal to 0. So now this is where that distance x is going to come in and it's going to change. So let's start with this 8 kilonewton meters, right? Moment is force times distance. So we know that we have this 8 kilonewton force rotating us clockwise. So we're going to subtract 8. And then we're going to multiply it by distance, right? Moment is force times distance. But our distance to the moment is x, right? That's an unknown. It could be any distance, and we're just calculating its distance from the wall to where we're taking the cut. So we're going to put in an x for that. That's basically our unknown. Then we have this 32 kilonewton meter force that's positive, so we're going to add 32. And then our moment here is also positive, so we're going to add m and set all of that equal to 0. So this is the m we're trying to write the equation for. So if we move everything over, we're going to find that moment is equal to 8x minus 32, and this is in kilonewton meters. So there we go, we solved the first part of this problem. We wrote the equations for each one of them. I think I did that right. Yes, I did. Okay. So what does this tell us, right? Well, this tells us that a moment, right, it's going to get bigger, right? It's going to get closer to 0, basically. It's going to start at negative 32 when our x is equal to 0. So when we're against the wall at A, it's going to start at negative 32. But then as our x grows, it's going to grow to 0. And then it's going to become positive because it's a linear slope. So let's go ahead and graph these now. That's what we're supposed to do. So let's start with the moment, or the shear, I mean. The shear is easy. Right, it's super easy to graph. Right, so let's label this x as in meters, right? We want our x-axis to be distance. Basically, we're looking at how far away from A have we gone. And then y is our shear in kilonewtons. And so it just is 8 kilonewtons, so we know we're going to stay at 8 kilonewtons the entire way till we reach 4 meters. And so that's our shear diagram. Very simple, right? And really quickly, you can make sure that this is right. We're supposed to end at 0 every time. And we can tell that because we have an 8 kilonewton force at the end here. So our shear is going to be negative 8 kilonewtons because it's pointing downward. So we're going to have an 8 kilonewton force pushing downward, and then we're going to reach the end, and this is going to cancel that out, basically. So that is why we always end at 0. So now we need to draw the moment equation, or the moment diagram. So similarly, our x-axis is going to be the distance in meters, and our y-axis is now going to be moment in kilonewton meters. So now when we're going to solve, we're going to plug in this equation, and we're just graphing this equation. We're just going to plug in points. So we're starting at x is equal to 0. If we plug in x is equal to 0, we're going to get negative 32. And then we know it's going to be a linear line, so if we plug in x is equal to 4, we get 0. So we're going to end at no moment. Or not that, but it's going to end at 4 meters, right? And it's just going to be a straight line from negative 32 to 4. And there we go. So we drew our shear diagram and our moment diagram. So that's how you write the equations. So this is a super simple problem, right? We're going to get into some more complicated problems next. So stick around for that, and I'll see you in the next problem. All right, we're on our next problem now. So this one's got a little bit of a step up to it. So let's look at this. We're given this beam, and it's fixed in at A again. And so let's look, what do we have? So we're going from the left to the right this time. So this time we're going from basically the end outward and moving our way to the wall. So it's different. So we have a 15 kilonewton moment acting at the end of our beam here. And we have a distributed load of 3 kilonewton per meter acting on our beam. So now I need to draw the shear moment diagrams, starting from the left and moving to the right. So you might need to think, okay, well, let's start by finding all of our unknowns. In this case, because we're starting on the end opposite from all of the unknowns, right? A is going to have a moment, a shear, and or a moment forcing the y, forcing the x. But when we draw, again, we're going to take a cut. So imagine I'm taking a cut, maybe right here. Everything to the right is going to get cut off a bit. We're not going to worry about anything over here as we move along. So we actually don't need to find any parts of A yet. So let's go ahead and just make a cut and let's analyze that. So drawing our force body diagram, here is the end. We're gonna go this way, and this is our cut right there. So let's draw everything on the cut, right? We're taking a cut from the left side. So our shear is gonna point downward, and our moment is gonna go counterclockwise. So we're gonna label that moment. Then let's draw in everything we know already. So we have this 15 kilonewton meter moment acting like this, 15 kilonewton meters. We have this 3 kilonewton distributed load. We need to keep it a distributed load when we're doing these force body diagrams. 3 kilonewton meters, right? And then this distance is x. So that's pretty important here. Label that distance x. So here's everything. So let's write out equations now for what our shear and moment look like. So we're going to take some of the forces in the y to find our shear, set that equal to 0. So we have this distributed load. Its force is 3 kilonewton meters per meter. So we're going to put that in, 3 kilonewtons per meter. Or I don't know why I said 3 kilonewton meters per meter. It's 3 kilonewtons per meter. And then its distance, right? We need to find out how many meters. We're looking for force, not distributed load. So to find a force, we need to multiply this distributed load times the distance. So its distance is x meters, right? However far we've gone, that distributed load is going to expand. So we need to multiply this x by that to make sure that it grows. So now what we have is an x in our shear diagram. So of course we need to subtract b, set it equal to 0, because b is also in the y direction. And what you're going to get is that b is equal to 3x kilonewtons. So as we go further down the beam, our shear is going to grow, and that makes sense because we have a distributed load. But that's telling us that as we go further in x, our shear is going to get bigger. So then let's go ahead and find the moment. So I'm going to grab my chair again. Now we're going to take some of the moments around that point and set it equal to 0. So what do we have? First of all, we have this 15. It's going clockwise, so we're going to subtract 15. Then we have this distributed load. So like we said, the force of the distributed load is 3x. So we're going to, first of all, let's make this one rotate counterclockwise. So we're going to add that. So we're going to move 3 kilonewton meters, 3 kilonewtons per meter. And then its distance is x meters. So what we found here is 3 kilonewtons times x. This is the force of our load. So as we grow, that force gets bigger. But when we're taking the moment, we need to multiply it by the distance it's gone. So the distance away from here. Now the distance from the point we're taking the moment at is going to be half of it because it's just a rectangle. So we need to take x and divide it by 2. So let's go through each point of this again. 3 kilonewton per meter is the distributed load. We multiply it by x to turn the distributed load into a force. So now we know the magnitude of this distributed load as a force. Then we multiply it by x divided by 2 to multiply, or basically to find the distance away from where we're circling around to the halfway point of the rectangle. And that's the distance away from the force. So we get left with this equation. Then all we have left is to add the moment. So the moment is going counterclockwise, so we just add moment. Set that equal to 0. Okay, I got confused because I forgot a negative here. So negative, it'll be minus minus, this will become a negative 3. So it'll be equal to negative 3. So this is correct. So then if we rearrange this equation, move everything over, you're going to get moment is negative 3 halves 3 over 2 x squared plus 15. So this is our moment equation. All right, so I've cleaned up, and let's go ahead and draw the shear moment diagram. So we're basically just going to be graphing this. So these should be really easy to graph. Let's go ahead and draw it. So our distance is 0 to 4 meters. So let's put 4 here, and this is x in meters. And then we're drawing the shear, so this is v in kilonewtons. So we're starting, basically, we're just plugging in points. At 0, we have 0 shear. But then at the end, we're going to go to 4 distance. So it's going to be 3 times 4. We're going to get to negative 12 kilonewtons, basically. So it's going to be a linear line to here, and then of course it's going to bounce back up to 0 as we hit that wall. So this is going to be negative 12. So that's our shear diagram. Now let's draw a moment diagram. this is x in meters again. This is moment in kilonewton meters. So now we're going to plug in points again. So if we plug in x is equal to 0, we know we're going to start at 15. So we're starting at 15. Now let's find out where we're going to end. If we want to find out where we're going to end, let's plug in x is equal to 4 meters, right? Because we're going to end at 4 meters, so we'll plug in 4 for that. You're going to get negative 3 halves 4 squared plus 15. What you're going to find is this is equal to negative 9, so we're going to end here at negative 9. And because we have this negative x squared, we know we're going to have a downward parabola. So it's going to be something like this is how it's going to look. But one last thing we can find basically with this moment diagram is maybe we want to find where this intercept is. Like, where is this x-intercept? The way we can do that is we can take that moment equation and let's set moment equal to 0 because that's where moment is equal to 0. That's our intercept. So we're going to get 0 is equal to negative 3 halves x squared plus 15. So from here you can solve for x and you're going to find that this is about 3.16 meters is that x-intercept. And there we go. So that's how we find our shear and moment diagrams for that beam. So let's move on to the next column. It's going to be a bit more tricky than this one. All right, we're on to example 3 now. So we have this beam, and it has a pin and a roller and one force acting in the middle of it. And our goal is to find the shear and moment diagrams. So you might be thinking, oh, this one looks really easy, right? But what we're going to have to do is we have to break it into 2 parts. So the reason we have to break it into 2 parts, and the last ones we didn't, is because anytime we have a force, a singular force basically acting, or any changes that take place in the beam, you have to break it up into before that force and after that force. Because you can imagine the moment and the shear is going to be different over here than it is over here due to this 1,000-pound force. So let's go ahead and let's find the support reactions, starting with that. So let's draw our force body diagram. Right, this is, I should label this A, B, and C, but this is A, this is B, and this is C. So here's A. Here's B, here's C, this is 5 feet, and this is 8 feet. So forces are A of Y, 1,000, pushing down, and C of Y. So let's start with one of these. So let's take the moment around A to find C of Y. So sum of the moments around A has to be equal to 0. So what do we have? Well, we have this 1,000-pound force. Should have put labels on that, but it's going to push us clockwise, so we need to subtract that 1,000 times its distance of 5 feet. Then we're going to add that to C of Y. That's pushing clockwise, so we're going to add C of Y times 13 feet, right? 5 plus 8 is 13. Set it equal to 0. Solve for this, you get C of Y is equal to, I did not label these correct, but whatever. C of Y is equal to 385 pounds. So then if you do sum of the forces in the Y equal to 0, you're going to get A of Y minus 1,000 plus B of Y, 385 is equal to 0. You get that A of Y is equal to 615 pounds. So these are good numbers to find. Now we're going to go ahead and take a cut. So we're going to need to take 2 cuts, like I said earlier. The first cut is going to be anywhere between A and B. So we're going to take here, and let's just cut there. And let's draw our reactions. So of course we have shear pointing down. Let's label that shear of 1, and this is going to be moment 1 because this is our first of 2. So we know what A of Y is. A of Y is 615 pounds. And then this distance is x, right? It's anywhere from x, and this is good to label on your paper. 0 is less than x is less than 4 feet. Or I guess this is 5 feet, right? This is basically saying we're in between A and B. We're anywhere in this section between A and B is where this cut is taking place. So really easily, sum of the forces in the Y equal to 0, right? So we're going to have 615 minus V is equal to 0. So we're going to find that V1, or I guess V1 is equal to 615 pounds. All right, then let's do moment. So sum of the moments around that point that we took the cut at is equal to 0. So let's add them up. So this 615 is making us want to rotate clockwise. So we're going to subtract that 615. And its distance away is x, similarly to the last problem. So as this x grows, that moment is going to grow. It's going to be a stronger moment as that x gets bigger. And then, of course, momentum 1 is going counterclockwise, so we add that. So then if you solve that, of course you just get moment 1 is equal to 615x pound-feet. Nice. So as you can see, you probably noticed this maybe already, maybe not. The shear is the integral of moment, right? If you take the derivative of moment, you should get the shear. And that's a very useful tool you can use in these kind of problems just to double check your work. Or maybe just to do less work if you like. Okay, so we can go ahead and get rid of this because we've already used it all. So now let's go between 5 and 13 feet. So now we're looking anywhere between B and C. We're going to take the equation and find it there. So this is now between 5 and 13 feet. So this is A, and we're going to go all the way to B, where we have that force acting, and then we're going to take a cut. So at B, we have the 1,000-pound force acting downward. And then we have, again, the shear. This is V, and then the moment. So this is a distance of 5 feet here, and then the total distance is going to be x, how far we've gone to that point. So let's go ahead and write the equations for this. So start with sum of the forces from Y, set it equal to 0. So we have 615 minus 1,000, and then minus V is equal to 0. Solve for this, you get that V2, right, this is V2, and this is moment 2. We're going to find that V2 is equal to negative 385 pounds. And then let's take the moment. So sum of the moments around that point is equal to 0. So let's do it. So we have the 615, like we said, it's going to be the same thing here. It's going to be negative 615 times its distance away from this point that we're taking it around. That distance is x, so we're just going to put in x for that force, is that moment. Then we have this 1,000-pound force. So this one is making us want to rotate counterclockwise, so we're going to add 1,000. And then what's its distance? So this time, we can't just use x. We don't know that full distance. We know that if we use x, it's going to be the distance from O to A. But the distance from O to A is not the distance from O to B. But we know that the distance from A to B is 5 feet. So what we can do is we can take this total of x feet and subtract it from that 5 feet, right? We just want this distance. We're just looking for how long is this segment. What we can do is we can take x and subtract it from 5 just to get the distance of this. So that's what we did right here. That's the distance away from O to B. Then finally, our last thing to add is that moment of 2. Set that equal to 0. So now what we got to do is we just got to move one of these over and solve. And what you're going to find is that, making sure I did this right, of course, is that moment 2 is equal to negative 385x plus 5,000. And as you can see, if you take the derivative of the moment, we get the shear. So now we have these 4 equations. So one equation for V1 and for V2, an equation for moment 1 and moment 2. So now we just need to graph these two as piecewise functions, basically. So let's see with the shear first. Is shear going to be, shear is going to look simple. So, right, this is x in meters, and this is shear in pounds. This is not in meters, we're in feet, by the way. I lied. Okay, so let's do it. We have a piecewise function, basically. V1 goes from 0 to 5 feet. It's between A and B. So we're going to go up to 5 feet. And it's going to be at 615. So it's going to be this, 615. Then we're going to drop down to negative 385 from 5 feet to 13 feet. So we're going to be down here until we reach the end. So we can go ahead and kind of draw it like this. This is negative 385 pounds. And then this goes all the way to 13 feet. And that's what our shear diagram looks like this. So now what we need to do is draw the moment diagram. So the moment diagram, this is x in feet, and then this is moment in pound feet. All right, so let's start. So we're gonna graph this function until we reach 5 feet. So we're going to 5, and then we're gonna graph this function until we reach 13 feet. So the first one is just 615x. So it's just gonna be a straight line starting at the origin. And where's that high point gonna reach? Well, we're gonna plug in 5 for x, basically. If we wanna find the height of this, which we do, all you have to do is plug in 5 for x, and you're gonna find that that height is 3,075, right? Then we're gonna go to this equation, and we need to graph this equation from 5 to 13. So let's start with our starting point, right? It's gonna be a linear line going downward. So let's start with our starting point. If we plug in 5 to this equation, negative 385 times 5 plus 5,000, what we get is this exact same number. So if we're starting here again, and then we're gonna go downward in a linear line until we reach our final point. Now to find our final point, we plug in 13 for x again. So negative 385 times 13 plus 5,000 is equal to 0. So that means that we're just gonna end at 0 just like that. And that's what our graph looks like. So yeah, solve example 3. This one's a little trickier because we had to break it into 2 parts, and you can see that's where the gap or the switch up comes from. All right, we're on to the last problem here. So we are given this beam here, pin at A, roller at B, or roller at C, and then we have this distributed load acting for half of the beam, only 2 meters it's acting. Now we need to find the shear moment diagrams for this whole beam. So this is going to combine everything we've learned so far, right? We have the distributed load, we have the forces of A and C, and then we also have this cut at B that we're going to need to do. We're going to need to do 2 sections similarly to last problem. So let's start with finding our support reactions. So let's find A and C. So when we're finding our support reactions, we can go ahead and simplify this distributed load into one force load. However, when we're doing the shear moment diagrams, we have to keep it as a distributed load because it's going to make a difference. So first of all, we have A of Y. I'm going to go ahead and not try A of X. Why? Because A of X is equal to 0. We can tell that because if we do sum of the forces in the X, it's going to be equal to 0. So go ahead and check me on that if you'd like. Now we're going to have C of Y is also an unknown. Now this 3 kilonewton per meter load is acting over 2 meters. So we're going to multiply 3 times 2 to figure out that it's a 6 kilonewton force. And it's going to act in the centroid between basically 2 and 4 meters. So it's going to be acting at that 3 meters. So this is 6 kilonewtons. And then we can label these distances to be 3 meters and then an extra 1 meter. So if we take the sum of the moments, all right, if we want to find C of Y and A of Y, let's say sum of the moments around A, set it equal to 0. So first of all, the 6 kilonewton load is making us go counterclockwise, so we're going to subtract 6 times its distance away, which is 3. And then we're going to add C of Y because it's making us go clockwise, times 4, set that equal to 0. This will tell you that C of Y is equal to 4.5 kilonewtons. And then if we do sum of the forces in the Y, it's equal to 0, right? We're going to have A of Y, which is unknown, minus 6, plus C of Y, which is 4.5, is equal to 0. Solve for A of Y. You get that A of Y is equal to 1.5 kilonewtons. Okay, so we found our unknowns. Now let's go ahead and take our cuts. So our first cut is going to be between A and B. Right, we're going to take a cut in this first section, and then we're going to have to look between B and C and figure out what that equation is going to look like. So first cut in between A and B. Say we take an N there. So we have A of Y, right? We figure what that is, 1.5 kilonewtons. And then we have our unknowns, right? Shear and moment. Right, these are our notations as we said earlier. So we want to write an equation for this. This is between 0 and 2 meters. So sum of the forces in the Y is equal to 0. So let's add them up, right? We have 1.5 pushing upward, and then V is pushing downward, and set that equal to 0. Forgot that this is distance x, by the way. So solve for this equation. This can be, let's label these V1, moment 1. So it'll be that the first shear is just equal to 1.5 kilonewtons. Cool, now let's find the moment by doing the sum of the moments around that is equal to 0. So of course we have this 1.5, it's going to rotate us going counterclockwise. It's going clockwise, right? So clockwise is going to make us negative. So minus 1.5 And then its moment, right? So it's going to be times its distance. Its distance away from that 1.5 is going to be x. So we're going to put in an x there. Then we're going to add our moment because it's going counterclockwise. We're just going to add it. Moment 1 is equal to 0. Of course, this is just going to give you that moment 1 is equal to 1.5x kilonewton meters. Similarly, take the derivative of this. You could v1 looks like we did it right. Okay, so now let's go ahead and look in between 2 and 4 meters. So basically get rid of all of this. 2, 4 meters. So here's that. Then we keep going, and that's where our cup is. So of course we're going to have shear, V2, moment, moment 2. And then we have that distributed load we have to consider, right? Looking at our force body diagram here, we have to add that distributed load. This is 3 kilonewton meters. 3 kilonewtons per meter. This distance is 2 meters from here to here. And then the distance all the way to the end is x. So this is how we draw this diagram here. Now we need to find out V2 and moment 2. So let's go ahead and do that. First of all, let's start with V2. So we're going to take sum of the forces in the line and set it equal to 0. So our first one, 1.5, is pushing up. Then we have this 3 kilonewton per meter distributed load. So that's going to be minus 3.5 or 3.0. Don't know why I did 3.5. Right, so we need to find the distributed load and convert it to a force. So to do that, right, we know how far it's acting for. It's 3 kilonewton per meter, and its distance is going to be that x, basically how far we've traveled minus 2. Right? The reason it's x minus 2, right, is we're looking for just this distance between here and here. If we want to find that distance, we can't just use x because x gives us this whole distance. So we're going to take that whole distance and subtract it by the distance that it starts at, which is 2. And that's going to give us x minus 2. So that's basically the magnitude of that force that's pushing downward. And we have to subtract V2, of course, so I can get that equal to 0. Make sure I did this right. Looks like I did. You're going to find that V2, basically by moving that to the other side, it's going to become negative 3x plus 7.5. So minus 3x plus 7.5 kilonewtons. All right, so then we have to find moment 2. So let's write the equation for that. Sum of the moments around O is equal to 0. So let's start with the first one. 1.5 is making us want to rotate clockwise. So we're going to subtract 1.5 times its distance, which is x, right? That's distance away from O. Then next we have this distributed load. It's negative, so it's going to make us want to rotate counterclockwise. So we're going to add that. So it's going to be, again, it's going to be its force times its distance away. So its force is basically what we found here. It's going to be that 3 times x minus 2. Again, it's the kilonewton meters times the distance it is to find the total force. Then to find the moment that it enacts, we need to take that and multiply it by its distance from the centroid. So if you can imagine, for the distance from O to the half point is going to be this distance. So if we want to find that, we need to take x, subtract it from 2, and then divide it by 2. We need to take basically the x minus 2 and divide it by that distance in half to find that. So then you're left with this, and we need to simplify this, and there's one thing left. We have to add that moment 2, and that's equal to 0, right? Because this moment 2 is also in the system, and that's how we find it. Okay, so now we just need to simplify this equation. So let's start with moving moment 2 to the other side. So we're going to subtract moment 2, but then we're going to divide by a negative 1. So we're going to be left with this moment 2 is equal to 1.5x minus 3, x minus 2, x minus 2. And let's go ahead and spring out this half and just make this 3 over 2. So then let's expand this. So this is going to be 1.5x minus 3 halves. Then this is going to become x squared minus 4x plus 4. So then what's going to happen is this is going to get distributed. And we'll find that moment 2 is equal to negative 3 halves x squared. Then this is going to become minus 3 halves times 4 is going to become 6, right? It's going to become 6, and then we're going to add it to that 1.5x to get 7.5x. And then this negative 3 halves times the 4 is just going to give us minus 6. And so this is our moment 2 equation. So now we have all of these. We have the shears for the first half and the second half, and the moment for the first half and the second half, and now we just need to graph them. All right, so let's start with the shear. So first of all, the first half of shear, right, it goes from 0 to 2 meters, and it's just equal to 1.5. So we can go ahead and start out here at 1.5. Then when we get to 2, it switches over. It starts at negative 3x plus 7.5. So first we want to find out basically what is our starting point, what's our end point. So V2, if you plug in 2 meters, right, we want to see what happens when we get to 2 meters. We get negative 6x, or negative 6 plus 7.5. So we're going to start at 1.5. So we're starting here, it looks like. Then we're going to go down, right, because it's a negative 3x, so it's going to be a downward linear line. So let's plug in 4 meters. So let's find out what happens at C. Where are we going to be at C? So we're going to go down 3, right? So we multiply this by 4. So you get negative 12 plus 7.5, and that's negative 4.5. So we're going to be down here at 4.5. So this is negative 4.5. And then we're going to bounce up to 0. And we found out that y is equal to 4.5 kilonewtons. So why is this the same as this? Well, it makes sense, right? We need the shear to be 0 at the ends of the beam. That's what the support reactions represent. So it should make sense that your support reaction is equal to whatever we are at the end of our thing. So one last thing we can add here, we can add the intercepts. It's pretty easy to tell algebraically that this is 2.5 is where that intercept happens at. Basically, you can also set v equal to 0 here, and it'll be 0 is equal to negative 3x plus 7.5. You'll find that x is equal to 2.5. So there we have the shear. Let's draw the moment. So the moment starts out at 1.5x for 0 to 2 meters. So that's pretty easy to draw, right? So we can go to 2, and this is going to go 1.5x. So of course it's just going to top out at 3. Then we don't know what's going to happen here. What happens is it becomes a parabola, and a downward facing parabola, negative 3 halves x squared plus 7.5x minus 6. So there's a couple ways. If you have a graphic calculator, you could use that. It's not allowed for some teachers, right? My teacher didn't allow it. So how else can we do it? Well, we can find its maximum, right? This is back to calculus 1. You should have known this for this, but basically we can take the derivative of moment and find where the absolute maximum is going to be. And the absolute maximum is where we can basically find when is it going to go from positive to negative. So remember that shear is the derivative of moment, so we don't even have to do that. We know that we're going to have an absolute maximum at x is equal to 2.5 from our shear diagram. It's going to go from positive to negative. So we can literally draw that in here. It's going to have a max at 2.5. That's going to kind of go up like that, and then it's going to start going back down. And if we want to find the maximum of this point, we're going to plug in 2.5. So we can plug in 2.5 here. It's going to be negative 3 halves 2.5 squared plus 7.5, 2.5 minus 6. And you're going to find that that point is equal to 3.375. So our maximum moment is going to be 3.375 for this beam. Then finally, we know it's just going to be a downward parabola until it reaches some point at the end. So what is that point going to be? Well, we can plug in x is equal to 4. So let's plug in x is equal to 4 for this. And you're going to find that it ends up equaling 0 at the end. So once we get to 4 meters, we're at equal to 0. And so that's what our moment diagram looks like for this beam. It goes straight line to 3, and it's a downward parabola until it reaches 4 and it touches 0. So yeah, that's how you solve these moment and shear diagram questions. They're pretty tricky, right? It's a very common question on YouTube. A lot of people are asking, a lot of people are having trouble with this. So if you're still having trouble, feel free to check out my channel. I have a lot of more practice problems in my playlist. Yeah, thanks for watching. Thanks for all the support, and I'll see you in the next video. Peace.